Okay, we're continuing with Chapter 1 in Basic Concepts of Medical Instrumentation. And in this section, I want to talk a little bit about biostatistics. So there are some important definitions and equations involved in biostatistics, and the first of these is the mean. So if we have a set of n measurements that we take, then our mean is just defined as the sum of all the measurements divided by n. The median is the value for which half of the measurements are above and half are below the mean. And the mode is the most frequently occurring observation. The geometric mean is often used with data on a logarithmic scale, and it's basically the nth root of the product of all the n separate measurements. The range is the difference between the largest and the smallest observation, and it's used to emphasize extreme values. And the standard deviation gives you a measure of spread around the mean. In general, you want at least 75% of your values to lie between plus and minus 2 standard deviations of the mean. If that's not the case, then it means you probably have an unusual number of outliers, and you would want to do something like either really look into your data to see if there was an issue involved with taking the data or an issue involved with the group you took the data on, or perhaps some kind of odd pattern in your measurement numbers. But you would definitely want to look at your measurement. Maybe you can do a transformation. It's not a lost cause, but you just, before you do a lot with your data, want to look and see that 75% of your values lie within 2 standard deviations plus and minus of the mean. And here's the formula for the standard deviation, where x sub I would be your individual measurements, x bar would be your mean, and then n minus 1 is 1 less than the number of measurements taken. The coefficient of variation is a way to standardize your variation so that if you have 2 different kinds of distributions, you can compare those two. So it's just the standard deviation divided by the mean times 100%. The percentile will give the percentage of a distribution that is less than or equal to the percentile number. The interquartile range would be the range from the 25th to the 75th percentile. Sometimes outliers in a data set are defined by standard deviation. Other times, so you would say if something is more than 2 standard deviations from the mean in either direction, it's considered an outlier. Other times, outliers are defined by use of the interquartile range. So if something falls outside of the interquartile range, it can be defined as an outlier. And finally, standard error of the mean is sort of the standard deviation of the means. So if you took a number of different sets of measurements and you took the mean of each of those, a measure of how much that would vary is basically the standard error. So it would be the standard deviation divided by the square root of n minus 1, with n being the number of measurements made. So we keep talking about distributions. The distribution is basically if you were making a measurement of a quantity, if it has some statistical variation, like let's take your weight. Let's say you weigh 120 pounds and you weigh every day on an analog scale. It's quite possible that your weight will have some slight fluctuations. Maybe you drank a big glass of water, maybe you're wearing heavier clothes, maybe you're not wearing shoes, maybe your scale is a little off, or the surface it's sitting on is a little uneven. But even if your weight stays relatively the same and you're not gaining or losing over the long term, you'll have an average weight, but then there will be a distribution around that average that will occur. So when we talk about a distribution, if you were going to plot, say, something like a histogram of your weight, there would be a spread around what would be an average, and that the shape of that spread is referred to as the distribution. Okay, well, a correlation coefficient, and here's where things begin to get interesting, because correlation coefficient basically gives you a measure of the relationship between 2 different variables, x and y. And it ranges from -1 for variables that are what we call anti-correlated to 0 for completely uncorrelated variables to 1 for correlated variables. And the way to calculate R is given in this formula here for the correlation coefficient, where obviously the subscript I refers to individual measures, the bar refers to the mean. So you're basically taking the product of the difference between individual measures of x and x bar and individual measures of y and y bar. You're taking the sum of the products and then you're dividing that by the square root of the sum of the squares of the individual um, differences. So what the correlation coefficient does is it tells you, is there a relationship between these two variables? So if I give you a certain dose of medication and I measure your blood pressure and then I change the dose of that medication and I measure your blood pressure again, does increasing your medication increase your blood pressure, which would give you a correlated variable? Does it decrease your blood pressure, which would give you an anti-correlated variable, or does it have no effect at all, which would be uncorrelated? Um, the important thing to understand is that all correlation really does is give you a measure of how correlated two variables are. It does not imply causality. So one of the issues with a lot of interpretation of data in the medical field, if we take the example I just spoke about for blood pressure medication and blood pressure, one of the issues that people can have is to make an assumption that the medication causes the blood pressure to go up or go down. Maybe if your blood pressure is lower, you're more likely to remember to take your medication because you're not stressed. So you really can't infer causality because correlation or anti-correlation are high. And that's a common mistake, especially you will see people in the media who make these ad hoc interpretations of medical studies and immediately infer causality. Magnetic resonance imaging is one of the classic cases where you will do something to someone and observe their brain activity and immediately draw a causal relationship when in fact there may not be a causal relationship that can necessarily be inferred. Confidence intervals and statistical tests. Now I mentioned early on that really each of these subject areas could comprise an entire course or part of a course, and there are entire courses devoted to biostatistics. So in mentioning biostatistical aspects of biomedical instrumentation, just giving you an overview here. So what a confidence interval does is it gives you a percentage, let's say 95% confidence, that the true value of the variable you're being measured, for example, of the mean, lies within the interval. So if I can tell you I have a 95% confidence level, I mean I'm 95% sure that that mean is going to lie within the interval that I'm specifying for you. So I say my average blood pressure is 120 over 80, and that would vary from 115 over 75 to 125 over 85, and I can say that with 95% confidence. And what I'm really telling you is 95% confident that my blood pressure mean is going to fall within that range. Hypothesis testing allows you to test the null hypothesis. In other words, you're always testing that something is not true. In statistics, it's much easier to say with confidence that something does not occur than to say it is occurring. So a p-value gives you the probability that something would occur by chance alone. Usually p-values of less than 5% indicate a statistically significant finding. So that would mean you had a confidence of greater than 95%. But if you're going to test a hypothesis, the hypothesis that you're testing is that that is not true. So in my little blood pressure example, I would be saying I want to test that my blood pressure does not fall. I'm going to say my blood pressure does not fall within the 115 over 75 to 125 over 85 range. If I do that test and I find that I have a p-value of less than 5%, then that means I have disproven the null hypothesis. So I have proven that that is not in fact the case. which would then allow you to infer that my blood pressure does fall within that range. Sensitivity is the probability that you obtain a true positive result. So when you make a measurement, so let's say we're testing your blood for the hepatitis C virus. That's all over the news right now. So we're testing you for hepatitis C, and we do that by a blood test. And it comes back positive. A true positive would mean that you got a positive result and that you really do have hepatitis C. So if you want to know the sensitivity, that would mean everybody that was tested has hepatitis C. And you're going to get some positives and you're going to get some negatives, but your negatives are going to be false because really those people have the condition. So your sensitivity would be true positives over true positives plus false negatives. So in a medical test, you would like a high sensitivity because the lower the sensitivity is, the more likely it is that you have missed diagnosing someone who has the disease but didn't get a true positive result on the test. So that's sensitivity. Specificity is the probability that you get a negative result in people that don't have the disease. So it's the number of true negatives divided by true negatives plus false positives. So in this case, this would mean that everyone I test does not have hepatitis C. And so I'm going to get true negatives, meaning they get a negative on the test. But then I might, for whatever reason, get some people who test positive who in fact don't have the disease. So specificity would mean the number of true negatives based on all of the people who don't have the disorder that you would get. So you're not going to have, if you have a high specificity, you're not going to have very many false positives. One of the kind of practical examples in life that yields a lot of false positives that has always kind of been a problem previously was in sort of the old school mammograms. People would see things on the mammogram that would arouse suspicion, and so that would lead to the diagnosis of some kind of spot or cyst or something, when in fact a lot of times it was just an artifact within the x-ray. So the specificity of mammography before the advent of digital and intelligent mammography was poor, and of course led. So the problem here is not a misdiagnosis. The problem here is that you introduce stress in having someone think they have a condition when in fact they do not. So you would actually like to have high sensitivity and high specificity. So static characteristics. These characteristics describe a DC or very low frequency behavior of a measurement system. And so these would be things like accuracy, precision, and resolution. So accuracy is the difference between the true value and the measured value. And it's typically expressed as a percentage of a reading or full scale. So there's a number of digits on a digital scale, or plus or minus half the smallest division on an analog scale. Precision is typically related to repeatability, in other words, how close are the measurements to each other. And resolution tends to be the smallest incremental quantity that can be measured, so millivolts, microvolts, etc. Resolution will give you a guideline for the number of significant digits to report. So I find that students in the sciences and engineering tend to be befuddled about the meaning of significant digits. The meaning of significant digits becomes clear when you're actually trying to measure a physical quantity. Now, accuracy, precision, and resolution are definitions that vary, and they vary based on the field that they're used in, as well as the specific measurement and the instrument. And so you will find different definitions in different sources for these three things. There is some additional commentary on this Wikipedia site that you can and should access to read over accuracy and precision. Here's a visual display from that site. This is a target. We've got somebody trying to hit the center of the target. Here's an example of something that would have low accuracy. In other words, they're not hitting the center. They also don't have great precision because as you can see, they're all over the map here. They're hitting all different areas. The second figure would represent low accuracy once again because they're not within the target zone. But this is good precision because you notice we have this type pattern here. So our precision is good, our accuracy is low. In a static calibration of an instrument, you basically are going to hold all of your inputs constant except for one. And then you vary the one that you're not holding constant incrementally, and you measure the incremental outputs. So the static sensitivity is the ratio of the incremental output to the incremental input. And this can change over the instrument's measurement range. You would like for it not to change, but it can change. And so static sensitivity is defined by this parameter GD. It's y sub d over x sub d, where yd and xd are incremental output and input respectively. So when you use incremental measurement, you can actually determine a best fit line, and you can fit a line to the points, and then that gives you a calibration curve of your instrument. That's best done by minimizing the sum of the square error. So basically, to find the slope of that best fit line, n is the number of measurements, x is the incremental variation of x, y is the y output. And so these two formulas will give you the slope and the offset on the y-axis. So basically applying these two for each value of x gives you m and b that will give you a best fit line. These two formulas are derived by basically having the formula of a line, taking the difference between an arbitrary line and each data point, and varying the slope and the y-intercept in such a way to where you ultimately minimize the error for every point, the square error, for every point between your line and your data points. So it uses some calculus to find the minimal error, but you do end up with these formulas that can be applied. So other static characteristics that can be defined are zero drift. This would mean that there's something wrong with the zero value in your instrument and all of your output values are shifted by the same amount. So it's not zeroed out at 0 equals 0. Sensitivity drift would be a change in the slope of the calibration curve. So that would be if your output over input ratio for incremental input suddenly changes at some value, which would be a drift in your sensitivity. So here's a static sensitivity curve. This top curve in A shows the incremental change in X, incremental change in Y, and then here's the best fit line. Here's your intercept. Here's your slope. It's delta Y over delta X sub D. And then notice at some point this curve is no longer a constant. So what that means is that this point right here where that change occurs is the limit of linearity of your measurement instrument. This bottom figure indicates zero in sensitivity drift. So if you look, first just look at the solid line, because that's the line that you actually want to design around. And so notice that at x equals 0, you should have this static variable value of y, which is your offset. If there's zero drift, what you find is this entire curve shifts up or down. So you can have positive zero drift and negative zero drift, but notice the slope remains the same. So you have some zero drift here. If you have a broadening of your sensitivity, normally you would have a sensitivity that would be basically based around your slope. If you have a change in that sensitivity and a change in the zero drift, then you would see that you have an offset, and then you have kind of a change in that slope. So it basically means you have this error but then how sensitive you are to the error is changing with respect to your input. So basic definition of linearity for a system means several ways you can express this. Basically, you have a linear system. If you input x1, you output y1. If you input x2, you output y2. So one part of linearity is that the sum of the inputs is equal to the sum of the outputs. And note here that your author has a typo. This should be an x2 on this input here. So we're basically adding the two inputs and saying if the system is linear, we just get the sum of the two outputs. Another definition of a linear system is that if we multiply the input by a constant, then we basically get the output multiplied by the same constant. So here is our illustration of what we refer to as independent nonlinearity. So you have this least squared straight line, and then you have what you would refer to as a tolerance band, meaning that there's some variation around the point where you are willing to accept an error. You can define that in a couple of ways. You can define it as a percentage of the reading, or you can find it as a percentage of full scale. And so when you're given a specification of a tolerance band, then you basically are taking whichever permits the larger error. So you may have some zero drift errors that would dominate at low values. At higher values, it's maybe your sensitivity drift errors that dominate. And so it just kind of depends on where you are in the measurement and what your particular measurement system is designed to do. Your input parameters are range and input impedance. The range is the range of input values that are expected to be input to the instrument. The maximum operating range is the largest input that doesn't damage the instrument, and it usually occurs in the linear range. Input impedance is the ratio of the voltage to the current at an instrument input. It can vary with frequency, but it is usually a characteristic of the input of the instrument. Input impedance is important when you have very fast measurements and your sensor does not have the same impedance as your measurement system. You can then get some issues based on input impedance.